Hello, and welcome to the presentation of the SIMS 2021 short paper, Maintaining Driver Attentiveness in Shared Control Autonomous Driving. I'm Radu Calinescu, and this presentation describes joint work with my University of York colleagues Naif Alasmari and Gleirscher. My presentation has three parts. First, I will describe the context for our research. Second, I will present an overview of our self-adaptive solution for improving driver attentiveness in shared control autonomous driving. Finally, I will present the synthesis of the discrete event controller at the core of our solution. Our research focuses on level 3 driving automation. At this level of automation, cars are provided with an automated driving system that can perform the entire driving task, but only within a specific operational design domain, for instance, on specific types of roads and in certain weather conditions. Because these cars cannot drive autonomously under all conditions, they must have a human user located in the driver's seat, receptive to requests to intervene from the automated driving system and able to respond to such requests by taking over the control of the driving task. However, ensuring that the human driver remains attentive after potentially long periods of fully autonomous driving is very challenging. According to a recently adopted United Nations regulation, the responsibility for addressing this challenge resides with the automated driving system. The regulation states that this system has to detect if the driver is attentive and to provide warnings such as optical and acoustic alerts if the driver is unavailable. If the driver remains inattentive for 15 seconds, the system is required to initiate a demand for transitioning the control from the autonomous car to the human driver. Finally, if this demand is ignored by the driver, the system is meant to initiate a minimum risk maneuver, basically stopping the car in the lane in which it is traveling. The regulation is not prescriptive about the technical solution used to achieve these requirements. Developing suitable solutions is left to car manufacturers and to researchers. Our project proposes a human-in-the-loop self-adaptive system for solving this problem. In the second part of the presentation, I will describe this human-in-the-loop self-adaptive system. As shown in this diagram, our system uses a range of sensors to monitor the driver's biometrics and the status of the car. An analysis module based on a deep neural network uses this sensor data to determine the driver's attentiveness level. Green predicts that the driver is attentive, red means inattentive, and amber stands for an intermediate semi-attentive level. Changes in the driver attentiveness levels activate a discrete event controller. This controller is responsible for switching on and off several types of alerts, optical, acoustic, haptic, and so on, and for adjusting the speed of the car. The objective of the self-adaptive system is to achieve an optimal trade-off between three factors. First, we want to minimize the risks due to driver inattentiveness leading to minimal risk maneuvers by the car. Second, we want to minimize the driver nuisance caused by excessive use of the alerts. Finally, we want to maximize the progress with the journey by avoiding unnecessary speed reductions. In the last part of the presentation, I will describe the synthesis of the discrete event controller responsible for the decision making within our self-adaptive system. The controller synthesis comprises three steps. First, we model the design space of all controller options as a parametric continuous time Markov chain. The parameters of this model correspond to alternative controller options. Next, we quantify the risk, driver nuisance, and journey progress associated with different states of this model. Finally, we use a multi-objective optimization technique to synthesize a set of Pareto optimal controllers. In the Markov chain used to model the controller design space, states correspond to different system configurations. In the initial state, the driver is attentive, the controller is inactive, all the alerts are switched off and the car travels at regular speed. Only transitions due to a change in driver attentiveness are possible from this state. For instance, the driver becoming inattentive is modeled by this transition to a state that captures the change in driver attentiveness level and in which the discrete event controller is activated. Once in this state, the controller has the option to activate any combination of alerts and to reduce the speed of the car. With the two types of alerts shown in this example, the controller has 8 options, including the option to do nothing. As a reaction to the alerts switched on by the controller, the driver may become attentive again, in which case the controller will switch off all the alerts and the system returns to the initial state. If, however, the driver remains inattentive for a configurable period of time, we use a timer to reactivate the controller, giving it the opportunity to activate further alerts or to reduce the speed of the car. There are 16 states in which the controller needs to act. These correspond to the driver being inattentive or semi-attentive and to the alerts and speed reduction being on or off. Given the 8 controller options in each of these states, the controller design space comprises 8 to the power of 16 different controllers. We synthesize suitable controllers based on the 3 conflicting requirements mentioned earlier. We want to minimize risk and driver nuisance and to maximize the progress with the journey. To quantify the risk, driver nuisance, and journey progress for different controllers, we define the values of these properties for each of the system states. As an example, the driver nuisance will be 0 when all the alerts are off, will have some medium value if the optical alert is on, will have a high value if the acoustic alert is on, and a very high value if both alerts are on. This slide shows a fragment of the same controller design space as before, but encoded in the high-level modeling language of the probabilistic model checker Prism, and starting with additional declarations that use the evolve keyword to specify the controller options. For example, the first of these declarations specifies the 8 options available to the controller in the state in which the driver is semi-attentive and the 2 alerts and the speed reduction are all off. Given this encoding of the design space, we synthesize the Pareto optimal set of controllers by using a multi-objective optimization tool called EvoChecker, which we developed in previous work. This plot shows the outcome of the controller synthesis for a 4-hour journey. Each point corresponds to a Pareto optimal combination of controller options from which the preferred combination can be chosen. The top left area of the plot contains low nuisance solutions. At the back there is the solution with the best progress with the journey, 4 hours of full speed travel, but this has the highest risk. Accepting occasional reductions in speed can lower the risk at the expense of covering slightly fewer than 4 hours of full speed travel within 4 hours of journey time. Similarly, allowing growing levels of driver nuisance can decrease the risk considerably, as can be observed in the right areas of the plot. This brings me to the end of the presentation. Our research has delivered a work-in-progress solution to improving driver attentiveness in Level 3 autonomous cars through the use of a MAPE control loop. In this MAPE loop, we monitor the driver biometrics and the state of the car. We use a neural network to analyze the driver's attentiveness level. We plan driver alerts and speed changes using a discrete event controller, and we execute these plans using a range of actuators. In the next steps of our project, we plan to use results from the verification of the neural network to calibrate its predictions, and we plan to improve the accuracy of the solution by synthesizing personalized, adaptive, and robust controllers. Thank you for listening, and I hope you will be interested to learn more about our work by visiting our project's webpage and by attending the Human in the Loop Sim session on Thursday, the 20th of May.